Okay, so we got a circular swimming pool. It's a really, really deep swimming pool, 9 meters. No, it's 3 meters. It's like 9 feet. Still, that's really deep. 3 meters. And a diameter of 14. This is a gigantic, I'm thinking above ground pool, right? This is huge. Okay, and the depth of the water is 1.5 meters. Here we are. Okay, 1.5. And acceleration due to gravity 9.8. Density of water is 1,000. How much work is required to pump all the water over the side? Okay, so do we just calculate the weight or the force for all this water here?
No.
Why not? Why can't we just take the weight of all that water and multiply it by the distance it has to go?
Because the force changes depending on how deep the water is.
The force changes depending on how deep the water is. Agree?
The work is changing.
The work changes because they move different distances. The
Okay, that's the difference. The difference is how far the water has to go. All right? So we can look at one typical layer of water because that all has to go the same distance. And for the typical layer, we can calculate a delta W. So delta W is going to be force times the distance. And what is the force equivalent to? What are we talking about when we talk about the force? The weight. Okay, the weight of this layer. This is the weight of the layer. And the weight of the layer is going to be the volume times the weight density. And the weight density will be 9.8 times 1,000. Or 9,800. That's the weight. That's newtons per meter cubed. Okay, and so that's our weight. That's F. And then D is going to be the distance that we have to move that layer of water. Force times distance. Okay, so what's the volume? What do we have? Volume of what?
cylinder.
Yeah, like a pancake, right? The layer is the volume of the pancake, so it's going to be pi r squared H. It's going to be our volume times 9,800 times D. So now we have to get some frame of reference here. So we can put our zero. So our quantity, the distance is an up and down distance, right? So we can put zero anywhere we want. We could put it at the top of the water. We could put it at the top of the actual swimming pool. Okay, it doesn't matter. So as long as we're consistent through the rest of the problem with where we've chosen 0 to be. So
Can we put it at the bottom of the pool?
yeah,
Where is that?
Because then your distance is going to be a difference. Your distance is going to be, that's okay. So yeah, it's just kind of trade-off, you know. So let's just, I think what we did last time is we put our x equals 0. We put it at the top. So let's just put it at the top of at the height of the pool, okay? And we'll say x comes down like this. Okay, so then what is our h going to be? First of all, so what's the radius? Is the radius constant or changing?
Constant at
It's constant at 14. So that's easy.
7.
Well, the diameter is 14. Okay, so it's not as gigumongous as I thought. Still a big pool. Okay, so the diameter's, so we got 7 pi r squared. What's the height?
dx.
Delta x. So that's our volume. Pi r squared delta x is our volume. Times the 9800 gives us the weight of that layer, or the force to lift it. And then what's the distance then that it has to go? So what distance does our typical layer have to go? X. If we put the distance from the top of the tank down to the layer, then that's how far it has to go, X.
That's really convenient. So we should just put X not at like the goal, like where we want everything eventually to be.
Okay, but so we'll see another problem where, you know, like if vertically you have a circle, then it's not as convenient to put X at the top.
What do you mean vertically you have a circle?
Vertically you have a circle. So if this is up and down, this is not convenient
Yeah, okay.
because now the equation of your circle is shifted.
Yeah.
It's still doable, it's fine, you can do it, but I think whenever you have circles like this that are vertical, it's convenient to put the origin in the center, regardless of where the height of the liquid is.
Makes sense. But if the top is a plane, we can put X equals 0 up there?
That's one choice, and that's a convenient choice. Okay, and so then this is going to be our little bit of work to move that layer up out of the sides. Because we got the volume times the weight density times the distance that layer has to go, x. So then that's going to be, and then we're going to pi 49 pi times 9800 x dx. And then x is going to go from what to what?
1.5 to 3.
Yep, the first layer we have is at the 1.5 from the top, and the last one's 3, so 1.5 to 3. And that would be that will pump all the water out the side, up just over the top of the rim. Okay, and now if there's an outlet that's 3 meters, whatever this is 3 meters. Then basically all those layers have to all go 3 meters further than they did before. So you could put your X starting from here at where you're pumping it out at the top, and then your integration would be from what to what? So for part B,
4.5 to 6.
that's right, from 4.5 to 6.
But then is our vertical X the same, or is it X plus 3?
Wait, why is it 4.5?
3, what? So it's 1.5, right?
Oh, yeah. No, it's 4.5.
So if we define X from up here, the distance is still X.
Okay.
Yeah, so because you're going, this is X. And then it's just that your limits of integration are different. Or you could keep defining X here. If you kept defining X here, then what would the distance it would need to go would be?
X plus 3.
X plus 3, and then what would your limits be?
The same.
Still from 1.5 to 3.
Cool.
Right, so you can change your point of reference, and that will change the limits of integration, but keep the integrand the same. Or you could change, or you could just leave the point of reference the same, and then the layers would be the same limits, but now the distance it'd have to go would be 1.5 greater. Both will give the same result. But you don't want to do both. You don't want to change. You don't change it. You don't add 1.5 to both, one or the other. Okay, questions on this one? So that's part B, and this is part A. No questions? Clear as mud?
This is good.
Clear as water in a swimming pool? Okay, let's try number 6, which also had lower. So this is similar to what we did before. So a trough is 4 feet long and 1 foot high. And the cross section is shaped like y equals x squared. Like that. So that's the trough, and then it's full of water, so water all the way to the top. Again, we're looking at a typical layer, right? A typical layer. Just like that. And so we want the work to get that typical layer of water out the top of the tank. So that for this layer here, a little bit of work is going to be the force times the distance it has to go. So it's 4 feet long and 1 foot high. So this is 1 foot like that. And so y equals x squared. So where is our origin for y equals x squared related to this trough? Where is the origin for y equals x squared related to how I've drawn the trough? Where will the origin be? At the top where the water's coming out? No, so the vertex, right? So here then is your, for y equals x squared, there's your reference origin.
You can call it a vertex if it's not sharp.
The vertex of a parabola?
Cool.
Yeah, maximum or minimum, the vertex, yeah. And most are not, right? Most are not sharp. Okay, so there's that. Okay, so we got this typical layer. It's going to be delta y equals FD. So what's the force? It's going to be the volume times the weight density. Same thing as the last problem. I'm just using that symbol now. So what's the volume of this? Pi r squared h?
No, it's length with depth.
Length times width times height times the distance it has to go. So the length is this. We'll call that the length. That's 4. The width is. I heard x. I heard delta x. Neither of which is correct.
Width is variable.
2x.
Radical y.
Square root of that.
2x.
Okay, it's from here to here
2x.
is 2x. Right? Here's our origin. This should be the same.
No. All the way across.
Sorry, this is not great. That's better. Now it looks like 2x will better. Right, so the distance, so here's our parabola. See your parabola right here. Here's your parabola right here. You've got to recognize what your coordinates are in these geometric situations. So from here, so we're really referencing that point right there on the parabola. So the distance from here to here is 2x because that's x. So now we've got 2x. So the width is 2x, we said. The height is delta y. And then the weight density, 62 pounds per foot. We do not need to multiply that by something because pounds is weight. So just times 62.
Isn't it 62 and a half?
They said in this problem, you say use 62. But yes, that's more accurate. Or more precise, I should say. Okay, times what's the distance that this layer needs to go to get out the top? Y. Agree with that? 1 minus y. So we got y and 1 minus y. So it's the distance from here to here is the distance that it's got to go to get out. Is that y?
No, it's 1 minus y.
1 minus y. Why? Because y is the vertical distance from the x-axis to our point. So where's y? Y is right here. This is y. So this whole height is 1, then we want 1 minus y is that distance that this needs to get out to the top. Make sense? So there's our little bit of work. Volume, 4 times 2x times delta y, times weight density gives me the force, or the weight of my layer, times the distance that layer has to go. Yeah, you gotta get the x out of there.
For the swimming pool problem, I had a different integrand. I had different limits, but I still got the same answer.
Right, because you can, the frame of reference, you can put the frame of reference in different places. Yeah, we talked about that. Okay, so we got to get this x to be in terms of y. What is x in terms of y? Right. Yeah, that one's easy because if y is x squared, then x is radical y. So we're ready to go. So the total work is the integral of all the bits of work, right? All the delta w's. From what to what? So yeah, it's going to be dy. So the first little bit is going to be at y equals 0, and the last little bit is going to be y equals 1. So yeah, so we're going to go from 0 to 1. 4 times 2 delta y, or sorry, radical y, times 62, times 1 minus y dy.
We're only going to have to calculate, right? You want us to evaluate?
What's that?
Are we going to have to evaluate on the exam?
Maybe. So that should be no problem.
Okay.
Actually get the integral by pressing math 9.
Ooh, don't tell me that. That's naughty.
So this is piece of cake integral, right? But you might get something that's one of the techniques that we learned, and you'd be responsible for that. Okay? So if you had to apply one of the techniques to do this, you may be asked to set it up, you may be asked to actually finish it out and solve it. And then if we did in this one, if we got all the units right, I think everything was in feet and pounds, is that right? So this would be foot-pounds. Any questions on that? Okay, so let's talk about a little bit about the exam, and then we'll work on some more of these. We'll look at total force, hydrostatic force, which is another way to practice all these same principles with a new context. Okay. A last chance for. Does this make sense? Any questions on this one? Okay, so in docs and assignments last night, I put up So the review outline reflects our approaches in class, what we covered in class. So this is what you expect for the exam. Okay, this bullet outline. Okay, for the arc length, let me point out that you should be able to reproduce and understand all the components and steps of the derivation of that formula.
Nice.
Okay, and that's clearly on the video. I said that on the video. So make sure that you understand that derivation as well as be able to apply it. Okay. So if you skipped over that when you watched the video, you need to go back and study that. Be able to just do it by yourself. That's very attainable. It's not difficult, and it's a very worthwhile exercise. Okay. But like I said, this reflects how we approach the material, what we focused on in class. This review outline is what you should be thinking about in terms of expectation for the exam. Okay? So I had that review outline, I wrote the exam, and then I found this stuff just as a resource to you. So review problems, start with number 3. All this would be fair game concepts and material for the exam, but again, this all came after the exam was written. So this isn't the exam with different numbers. This is just stuff that applies, okay? This is just stuff that applies. And you can work all the way through from 3 through 20 on those practice problems. Don't do 1 and 2, don't do the last 2. We'll do that starting Thursday. And then the answers are there, okay? Don't look at the answers when you're solving these problems. Do your best. Pretend they're exam questions. Give final answers. Do whatever kinds of checking you could do on your own. And as a very final step, then check your answer. Okay? It's not good practice to look at a solution or look at an answer and working backwards. And you're like, oh, I get it. No, you don't. Okay? So just only use the answers as a very final check. And if it's not right, don't try to work backwards. Forget that you looked at the answer and try and go work on it again. Okay? And then there's an old 266 exam. Again, this came after the fact that your review and your exam was written, but there's a lot of applicable stuff. So also, when you will see things that don't apply to our material. So I'll just leave that up to you to determine if we did it or not. All right, so you should know that, okay? By looking at a problem, whether we covered it or not. But most of it we covered, okay? So that's more good practice. Again, that test is not our test with different numbers. It's totally different. To get your best, to form your expectation of our exam, it's the way we approach things in class, the problems we did, and then this review outline. Questions about our exam tomorrow? Again, it's some multiple choice and some free response. Okay, so let's talk about hydrostatic force, which is more practice of this physics stuff. Okay. So what happens is, if you have some kind of surface beneath the surface of some liquid or like in the ocean. So if you have some kind of liquid like this, and you have some kind of vertical region R, like a plate, wall, etc., that's submerged, okay? The pressure, the pressure of being submerged puts a force on that plate, But the amount of pressure varies with depth, right? So the further that you go down from the surface, the greater the pressure is. So then the greater the force would be as you go down on that vertical surface. Does that make sense? Is there a question?
Is pressure just force applied over an area?
Yes. Yeah. Okay, so the pressure on the plate varies with depth. The deeper you go, the more pressure. So at the surface, pressure is 0. And then the deeper that you go, and it's actually just linear, right? It's just linear. So pressure equals the weight density times depth. So weight density would have units of newtons per meter cubed or pounds per foot cubed. And then depth would be units of newtons, or meters or pound or feet.
So pressure and depth are directly proportional.
Pressure is directly proportional to depth. That's right. Something like this. So it's P equals. So they use rho. So weight density. So isn't that rho? Rho times d. Again, if you're in metric and they give you the mass density, you're going to need to multiply by 9.8 to get the weight density of the fluid. So basically, our pressure is the weight density times depth. And so then the units of pressure would be feet, pound per foot square, or newtons per meter square, or pounds per square inch. Okay, so those are all units of pressure.
Wait, which one is rho? That's the P looking thing?
Rho. Yeah. Weight density times depth.
It's like a P with the hook.
Yeah, it's that. Greek rho. Okay, so units of pressure could be Newton per meter squared, pound per foot squared. So the most common one you see is pound per inch squared, or PSI. And then force then is, how would you get force from pressure? If pressure is weight, force per,
Multiplied by the area.
yeah, you're just going to multiply by the area, and that's going to give you the force. So therefore, force equals pressure times area. why does the force on region R require an integral? Why does calculating the total hydrostatic force on this vertical surface R, why does that require an integral?
Because it changes
What changes?
the bits of pressure or
Changes.
force depending on depth.
Right, exactly. So your pressure is going to increase with depth, therefore your force is going to increase with depth. So to add up all the force, we're going to have to break it up by depth and sum up all the little bits of force at different depths. Yeah, Mike, go ahead.
Going back to the units of pressure, shouldn't they be in cube?
Nope, that's density. So our weight density is cubed, and then pressure is two-dimensional, right? So it's like how much pressure is on a two-dimensional surface. So it's how much, so if you take an area, it's how much force per unit of area. It's how much force you have per unit of area, that's why it's squared.
Okay.
Does it make sense?
Yeah.
So PSI would be, if I could draw an inch squared here. Too big. Still a little too big. So PSI is how many pounds are pushing on that much area, right? 1 inch squared. How many pounds pushing on 1 square area of, or 1 square inch of area? So like a bike, like a racing bike tires, is something like 90 or something, right?
85.
What is it?
Mine's 140.
120?
Way.
Yeah, so
Jeez.
it's a really high pressure in those tires because you have like around 100 pounds pushing per that much area. That's how you measure pressure.
That'll pop if you-
Okay, so you've got all the basics of setting up integrals. You've got all the basics of hydrostatic force. So let's see if you can do one by yourself. Ready? Here we go. Find the total force on a So I'll just make the picture. Okay, so we got water here. And let's say this is so this is, say, 5 meters below the surface. Say this is 4 meters. Let's say that's 8. And it's in the water. Okay, so you got your crash course in hydrostatic pressure. You're experts at physics applications. You got all the tools you need. Let's do it in your notes and do it on the sheet.
Does the plate have a thickness?
Sure, what do you want it to be?
7.
7? 7 what? So you mean like a thickness back into the board, say?
Yeah, I was just curious.
Will that make a difference? Like if it's a thin plate versus a thick plate, does that change the water pressure on that surface, on that region?
Only the depth.
No,
It doesn't object will change it.
Single factor.
What's that?
Oh, nothing.
There you go. Yep.
Oh, this is that high.
Okay, I'm gonna do this because I should have given you more direction in terms of the frame of reference. So when you do these problems, if you really want, what I recommend is put do that. Make this positive y, so then y is the same as depth. Okay? And I should have told you that, so that we were all doing the same thing. So everyone figured out a different way to do this. So I apologize. Okay, so this I think this is a good way to do it. So make your positive y down from the surface, and then it's the same. Y is the same as depth. Then y equals depth. You don't have to do the opposite. No negatives. Okay, and then we'll do x out to the right like this. Okay, so I think most of us got to the point where we knew we're gonna look at the force on a typical strip because the pressure doesn't change for a very small change in depth, right? So that's going to be our delta A right there. Okay, and so the pressure is going to be, what do we say, weight density, 9,800, 9.8 times 1,000, times the depth, which will be y, right? And then the force, a little bit of force, is going to be our pressure times a little bit of area. So what's the pressure? The pressure is our 9,800 y. And what's the little bit of area? What's going to be length times width?
Y over 2.
So what is length, width times height, I guess.
So the height.
The height is going to be delta y. And the width is going to be,
X.
You gotta find out what's that.
2x.
yeah, so we could just, we could find the equation. So there's two kind of ways to approach this. We could find the equation of that line, and then the width would be 2x. Okay? Or we could just make our relationship width, depth, y, and w.
Yeah.
Just do it that way.
That's what I meant by line.
Yeah, so either way. So if you find the actual equation of that line in this coordinate system, then that width is going to be 2x. Or you can just make a linear function of y and width. So if we're doing that, then when the y is 5, the width is 4. And when y is 13, the width is 0. So then our delta w over delta y is negative a half. Okay? And so then we would have w minus 4 equals negative 1/2 y minus 5. And w equals negative 1/2 y plus 5/2 plus 4. Or negative 1/2 y plus 13/2. All right, did I lose anybody? So what did I do? I just figured out what the width was at any depth, right? I figured out what the width was at any depth. Width as a function of depth.
So W minus Y. That's
4. W minus 4. I'm plugging in the point 4 or 5. I'm using the point 4 or 5. So let's check it. At a depth of 5, do I get 4? So I get negative 5 halves plus 13 halves is 8 halves. That's 4. At a depth of 13, do I get 0? Yes, it works. So I get 5 comma 4. Check. 13 comma 0. Check. All right, so then my area would be the width times delta y. And now I got my width, which is negative 1/2 y plus 13 halves. Times delta y. So that's my little bit of force. Pressure, 9,800 y times delta A. So putting that system in a different place might make this easier, but then this would be a little more complicated. So it's like trade-off, right?
Yeah.
So by putting it here, the depth is easy because the depth is just y. But then that relationship of width to depth is more takes a little more work.
If you start from the top, then your line is a lot easier to find.
If what?
Like if you have your x or your y equaling 0 at the top of the plate.
Or no, here. So the easiest way to find that line is if you put x-axis here and y-axis there. Then that's the easiest way to do that line. But then your limits are weird because you're starting under the water, and then this is different too.
Yeah.
So I think for these, I think this is the way to go. And I should have told you that before you guys started.
So then here you're just going 0 to 13.
What's that? So then your depth goes from what to what? So the total force
5 to 13. 5 to 13.
equals
Yeah.
the sum of all the little bits of force, which is 9,800 y times negative 1/2 y plus dy. And that's going to go from what to what? So we're going to sum up the y's go from 5 to, not 8,
13.
5 to 13. Okay, please ask if I lost you, if you have a question.
So these are going to be like horrendous to grade if everyone's using different approaches.
So, do you want to help me grade?
Yeah, actually, yeah. That's not okay.
Questions on this? Anybody? So yes, some of you use different frames of reference. You put the origin somewhere else. You make y go up. It will still work, but then I think the limits are harder, and then the depth is harder to make sure you got that right. So I think this way the depth, you get the limits are easy, the depth is easy. It's just you got to get that width as a function of depth correct, which that's the slightly harder part.
Could you just go through that one more time real quick? Just finding the delta A part.
So delta A is width times delta y. You get that much?
And that's because you're using a rectangle for typical.
Yeah, just like in all the other problems we've done so far.
Yeah.
So width times delta y. Just a rectangle.
Yes.
Okay, so then that width is a function of y. And it's a linear function because this is straight. It's not a circle, it's not a parabola, but it's a triangle, so that's a straight line. So the width varies with depth. So when depth is 5, width is 4. When depth is 13, width is 0. And that gives me my points to set up the equation.
And so,
Tyler.
So what is the integration relative to the shape and not the actual x?
So relative to how you set up your frame of reference, you're doing dy. And so y is our distance down from the surface of the water. So we want from the first element to the last element. Where's the first element in terms of y? Where's the first element occur? It's this widest area right there, y equals 5. And then the last element is the point element at 13. So it's always however you define y in the problem, you're going to go from the starting element to the last element of that variable.
Did you use the second one because it didn't have an x? You thought it was 0? Or should I make it easier?
Did I do what now?
For the width? Did you
I
use
got my two ordered pairs, and I just found the equation of the line based on the two ordered pairs.
So I could have used the first one too? Or that's not
Here, this is any pair on the line, so I could use W 0, 13. Is that what you're saying?
Yeah.
Yeah,
So
so
I could have used the other one, the 5. Or not the 5, but because it's 0.
I
That's not
used the ordered pair. I used the ordered pair 5, 4. You could have used the ordered pair 13, 0. You could have used 13, 0.
Okay, so it could have been both.
This is the point slope equation of the line,
Okay.
which requires any point on the line and your rate of change. This can be any point on the line. And if you can see very quickly, I should have used the other point, right? So if I had 0, 13, I would have gotten negative 1 half y plus 13. There it is, 13x. Same thing, it's the exact thing. Same thing. That would have been easier if I used the other point. Other questions?
You're not gonna submerge like a hexagon, are you?
That would be too easy, right? So I'm thinking like a pentagon, maybe? Thanks for the idea. So
No problem.
let's do a pentagon on the test.
Oh my god.
All right, I want to do another example here. Any more questions about this one?
Will you provide the crazy areas for me?
Okay, let's go on.
Alright, come on. Good.
So we have a tanker. Okay, so this is our tanker, okay, and it's filled 3/4 of the height with gasoline.
What are those things on the bottom?
Wheels.
Come on, this is the back of the truck, right?
Oh, it's
You can't see it? Oh.
You gonna push it off? It can grab 360 degrees.
So it's filled with 3/4 filled with gasoline, and so the diameter of the tank is, what's the diameter of the tank? 12 feet. Okay? The length of the tank is 74 feet. Is that too long? No, that's all right. That's fine. And the water level is 3/4 full. No, not three by volume
by
of height.
3/4 of the diameter, right?
Right. So it's 3/4 filled by height, not by volume. Okay. So I want you to find two things. So what is the, and I need to give you the weight density of gasoline. I'll do that in a second. But what is the total force of the gas on this side of the tank? So what's the total force on this side of the tank? And then how much work would it take to empty this out of the top of the tanker?
on the pink thing?
No, we're going home. Enough time. So say our spout is the emptying spout is right there. I don't know why, but that's where it is.
So is it water or gas?
Yes. Is that a right water for?
Yeah, water level.
We have
Fluid
density.
level. Yeah, I'm going to get to that. So we'll just make this written homework. My intent was to do this in class.
Is the little spout like very top?
The very top. The very top high point.
This is the same we can just do rectangular slivers.
So let me get you the.
What is the density?
Yeah, I'm going to get you the density of the gas, and then we'll be good. So we need weight density of gas. Of course, it's in. Oh, I asked for weight density. They gave me a mass density. So.
Put weight density of petrol.
Oh, great. Gasoline. There it is. 44.9 pounds per foot cubed. 44.9. Okay, so you got just that one. I won't no web work, just this one 2-part written problem.
No, but
No, Stever. So with circular problems like